All right, so we're going to talk to you about, I'm sorry, the talk came together at 2 a.m. the day of the CFP, so we work with Fast and Furious as a theme. You're going to bear with us on this, right? So we're going to talk about the adoption of OpenTelemetry with the injector. We're going to have you go through this with us. We have 3 speakers today. Antoine Toulme here, Michele, and Jason. Rules of the road, so please take your phone out. You're going to be taking pictures today. We're going to be scanning QR codes. We have many QR codes for you. All of them are safe, which, sorry. Thank you. We'll take your questions at the end. Thank you. All right, let's start with OpenTelemetry. So this is a rendering of OpenTelemetry, of course, as you can see it. OpenTelemetry, so in 2019, the job here is to unify observability, starting with traces, then metrics, and logs, profiles, and we're working really hard to make this a suitable vision for the ecosystem so we can grow the pie, so we can make everybody kind of have a uniform approach to observability and how we want to everybody have a good time with it, right? So observability is a specification, it's an API, it's a set of SDKs, a set of tools, it's a set of Kubernetes solutions, and it all comes together as an experience so people can enjoy, right? And a big portion of that, of course, is all the APIs and the SDKs that we ship, right? So if you go to that talk in 2023, you can see this man here doing this, talking about the Java agent and how the Java agent of OpenTelemetry can allow you to have auto-instrumentation so that you can do all sorts of things magically without changing your code, right? And you can use what is bundled and possible with the Java runtime, with Java tool options and the Java agent command line argument. You can apply the same thing in Node.js, right? So you pass in some arguments as part of node options or when you run your node command, and that allows you to do a pre-compile phase or pre-interpret phase where you can weave in some actual code to interpret. You can do the same thing in .NET, that's the big chunk in the middle right here, or you can do this, it's just for fun, in Ruby, right? That's a Ruby option. All right, so this is way too hard, okay? We need simpler solutions, and we can't just like have operators just do CGI level things like, you know, being cosplaying green, trying to make things work in the back. So some requirements, we're gonna have separate deployment and instrumentation. We're gonna have a catch-all for anything on the system. We don't really care. We want to get everything instrumented. At this point, we just want to get more data. And we want to have a simple installation story. It needs to work in less than 5 minutes across all your boxes. It needs to be simple. So first, we said, OK, let's set some environment variables at the system level. Using systemd, there's a clean way to do this. It's really nice if you know systemd, which not many people do. So, OK, job done, right? Let's hop on the planes, party time, right? Well, not so fast, right? No one's actually using systemd to run Java applications in the year 2025. It's not happening, right? And we didn't save so much effort because now we're explaining systemd to operators who are not having a good time with this. So that's when Michele comes in and talks to us about how to do from code to runtime.
Hello there. Raise your hands if you run applications on Linux. Keep your hands up if you have a very good mental model of how your executables actually start. Very good. So this is like, I would have done this so fast in 2023. So I'm going to share this knowledge with you from the source code to the launching of the application so that you can have an accurate mental model on what I'm going to say next. So it's going to be nerd, but you know, bear with me. So we start from the code. And then we take a compiler and compile something, an object module. This is the name that you would have in C, C++, but in reality, like bytecode in Java is very similar, core serial runtime is very similar. So you have something that is kind of executable. Not really, because it's seldom self-contained, so you need something called the linker. The linker will take your code and merge it with other libraries. Some examples of those, like static libraries, you may want to reuse pieces of code that you may want to reuse from somewhere else. And then you have the binary. This is the kind of thing that, like the ls binary on Linux. Now, is ls self-contained? No, it's not. So it needs, at the very least, a kernel to talk to. The kernel controls, for example, file system access. So it needs to effectively invoke the kernel, but there is more. In reality, most binaries that we run in our containers, on our Linux hosts, they're actually dynamically linked, meaning that when the process starts, the operating system maps, as it loads the program, additional libraries in memory. And does any of you have some example of these libraries? Jurassic, what do you say? LD preload is a way to hijack the process. For example, libc, yeah? OpenSSL, that we love to hate, right? They're all dynamic libraries. The entire concept of a Linux distribution, arguably, is the system to share the kernel and the libraries and the user space so that you have one copy of OpenSSL, one copy of libc, which you can update separately. If you remember Heartbleed from a decade ago, having a distro where you could just replace OpenSSL without rebuilding all your binaries was a great thing. And that is dynamic linking. And dynamic linking is where we do our OpenTelemetry Injector shenanigans. And how does that work? Well, we mix, on load, the executable is mixed with system libraries, so .so files, such as, we spoke about it, libc, OpenSSL. And the executable, like how does the operating system know which libraries to link? That's because the executable has a list inside in the dynamic, in the DT needed symbols in ELF of what it needs. So that, for example, the operating system will know if it wants a libc or GNU libc or Muscle, OpenSSL, and so on. And you can actually, from the outside, hijack the process of which libraries will be bound with something called LD preload, which is something built in the linker. So you can add additional things. And with these additional things, you can override functions provided by the libraries. And if you remember the slide that Antoine was showing with all those environment variables, you can probably guess what we want to override, right? We want to override getenv, which is the function in libc that pretty much every runtime on Earth is using to look up things like Java_tool_options, Node_options, Python path, and a bunch of very funny things, as well as the location in memory where the environment is actually stored. Technically, it's linked to an array of strings, but bear with me. That's a location in memory, and then you know how to read it. And by finding a way to hijack these two things, we can change the environment as seen by the process. So it means that with the right override, we can get a Java application to start the OpenTelemetry Java agent without you doing anything about it, which is pretty cool. If you want to know more, I gave a talk at KubeCon London, where I go in excruciating detail about this, and you can also hit us up later. Now, doing LD preload is not exactly trivial, especially when you're doing it in a way that has to work on all possible containers, all possible applications. And for example, you must have your LD preload object to be libc independent, because you will never see an explosion as big as when you try to mix an LD preload with GNU libc on a binary with Muscle C or vice versa. It's like it goes up in flames. It's wonderful. Second, we learned the very hard way that if your LD preload binary is requiring symbols from the outside, if itself needs to borrow functionality from somewhere else, somebody somewhere has a dynamically linked executable without those things. Do we have anybody here for the AWS CNI plugin? No, because you owe me 3 nights of sleep. So there are dynamically binded executables that do not bind a libc, do not bind OpenSSL. I could not figure out what it wanted to be bound, but it's not binding the stuff expected. And then if your LD preload object is saying, hey, I want getenv from the outside, and there is no getenv, do you think your executable starts? It does not. So we had to figure out how to avoid that. And then it turns out that exposing dynamic symbols is also problematic, because then you can have other things that want to override them that doesn't work. So we came up with something that is going to land in a PR soon that is very, very cool, and it uses ELF. ELF is the way that in Linux you describe metadata about the application in terms of, for example, where the memory locations are, which dynamic libraries it wants to have loaded, where you are going to find particular functions. And I'm going to now bring you through the steps of how the injector does its magic. It's not, when you look at the code today, it's not there yet. You can look up in the Dusted operator where we are guinea pig testing the injector instead of upstreaming it to the community right away. But it's pretty solid. We have had 0 bug reports in months. And this is the initialization logic that makes the magic when you add LD preload in the mix. So first of all, the injector will go and look up where the ELF program header is. Usually it has 0040, but it's not 100% guaranteed. So we need to go and find out where to start reading. And then we go and crawl through ELF and find out which libraries want to be bound. Because as we found out the very hard way, not every dynamically linked process links a libc. So first of all, does it need a libc, and if so, which one? Because there are OpenTelemetry SDKs out there, specifically Python and .NET, that want different versions of the SDK to be loaded depending on whether your program, the runtime is compiled for libc or muscle, which is great fun. Then, after we know which libraries we care about, then we figure out where they are in memory. And this in Linux you do by reading the proc self-map file, where every single loaded library and memory location is available in a range in the memory of the process. After that, we go and find the dlsim function. Dlsim is a function in the libc or the loader, depending on the flavor of libc, that allows you to look up other symbols. So it's effectively our staging ground to, in order, find out what is environ, find out what is setenv, and then use setenv to attach additional data to the environ from the environment variables we care about. And this is how it's done. It just works. It's fantastic. If we do not find a libc, the injector does nothing. It's very safe. No libc, then it stops. It says, hey, I don't have a way to find environ. And now the interesting bit is, can you guess in which language we built the injector? You already know. You're cheating. Do you think it's C? Raise your hands if you think we did it in C. Thank you for the confidence. I'm not man enough to code against the headers of Linux for input-output. We actually did it in Zig. Zig is a very interesting language because it has a standard library, so you can do input-output and all types of mischievous things without depending on a libc. Remember, we cannot depend on libc. In Rust, all the targets have a libc dependency. In Go, technically, the standard libc doesn't have one, but if you want to expose something with the C ABI, then you must use Cigo, and Cigo will link libc, and then I'm screwed. So we went to Zig. It's a nice experience to build shared objects. It's very easy to set up. It has manual memory management, which I know that in this day and age sounds like barbarism, but for something that you want to embed in a process, knowing exactly how much memory you're going to allocate at any point in time is better than the alternatives. Like writing an LD preload object feels a bit like embedded software programming. And last but not least, we had a lot of goodies from the standard library about parsing ELF metadata, loading libraries, so we could just copy some functions, and we saved a huge amount of bugs by doing so. And now Jason is going to show you how it actually works.
I need someone to hold this mic, though, because I need two hands.
Okay.
All right. Hi, I'm a lowly operator of software at scale, and these are my microservices. I'm going to do a brief demo. You have to squint a little bit and pretend that I have these three VMs running in the cloud. On the upper left there is the main kind of entry point web service. It's written in Java. It's being deployed as a WAR file into Tomcat, which I think probably a lot of you have done before. And then on the right-hand side is a separate VM running two Node.js services written in Express. They get tied together. There's also a collector going to be running on each box, and it's configured to send telemetry to a third VM, which is running Jaeger. So switching gears, let's fire some stuff up. So first, on that bottom VM, that's just Jaeger. It's not going to do a lot other than what you're seeing there. And I'm going to fire up the collector on that instance, and I will fire up a collector on that instance. Okay, they're up and running. I'm also going to fire up these two microservices running Node on this. So there's a driver service that returns information about various drivers. There's one that can return information about cars. And similarly, and I should have done this first because it's a little bit slower, I'm going to start Tomcat. It is a little bit of a dig. We've all ran Tomcat. Come on. So let's take a look at the everyone's favorite file name here, Catalina.out. Yeah, cringing. I know. It's bringing it all back, isn't it? Okay, so hopefully that's coming up now. We can get a brief demo. If I do a refresh. Lovely. So you can imagine with this random car that we've returned and this random driver, you could build a whole franchise around this, right? And you've got a button here to renew. It's generated a few requests, and we can confirm that like nothing exciting is happening here. There's no instrumentation whatsoever. If we go back to our collector, nothing exciting is happening there. So I'm going to shut these services down. If I don't use backticks, might work. And we'll do the same thing over here. Kill that one, kill that one. All right. Then in this directory, I have the OpenTelemetry Injector Debian package. So I'm running Debian. I'm going to do a sudo dpackage-i to install the OpenTelemetry Injector Debian package. On that instance, I will do the same thing over here. Live demo. All right, so that has installed, and I will just become the root user because there's one additional step, and this is outlined in the README of the Injector repo. You need to write this little library path into the etc LD preload. And if we look at, I guess there's one other interesting thing to look at here. And that is now that I've installed the package, we get this OpenTelemetry directory. And then there's a config file that controls the behavior. And it's got specific configuration for each of the instrumentation libraries. All right, so our collector's still running. Let's go ahead and start up our Apache again. And while that's going, I'll do the same thing over here. So I installed the deb package. I have to do the magical incantation. Now that that's set up, we'll come over and restart our drivers. We'll restart our cars. And we'll just peek in our collector a little bit. And if the live demo gods smile upon us, maybe Tomcat will come back up. I guess we could check on that as well. It's not Catalina log, of course, it's Catalina out. Okay, so hopefully there's some OpenTelemetry stuff being spewed in the console, but let's find out if it's up. Is it up? Okay, all right, so the service is working again. We're able to get these drivers, we're able to get these cars, we're able to build an entire movie franchise. And let's go over to the Jaeger UI. Let me peel off previous work I was doing and show you what the Jaeger UI looks like. Okay, so it's showing our services now. We're getting some live telemetry. We find some traces. The first one here has 5 spans. And we notice that I didn't manually install any instrumentation libraries, right? This is the injector. And we've gotten 3 microservices stitched together just by running, installing a Debian package and running, one command to configure LD preload. So that's an applause time. Yeah.
All right, so I've seen how relaxed you were, and it's good. So we did something that is actually remarkable, adding OpenTelemetry when there was none, and it felt like, sure, why not? In reality, when you go and look at how it feels today to go and install OpenTelemetry packages, it can be much more complicated than that. And the injector is supposed to make this part boring for you, which is good. Now, what do we do next? So you have seen that we did some Debian packages, whoops. And we also have the equivalent for Red Hat. One of the things that we want to do is to go and improve the user experience for the Kubernetes operator for OpenTelemetry. So today, when you actually want to go and automatically inject instrumentation in your pods, it does not use the injector. You are supposed to create a resource that declares that in this particular namespace, you want applications instrumented in a certain way. But then you need to go and annotate the pod specs of your pods with annotations about what you want to have injected. And that is a lot of toil, can engender a lot of confusion because you may no longer remember which specific version of .NET or Python or Java you're running in this specific container. And for example, if you're in a situation where you have 2 containers and one has .NET on libc and one on muscle C, then you are out of luck. Then you're going to inject in one of them the wrong thing. And what we want to do is to get to the point where this is no longer necessary, which is very cool. Something else, which is pretty exciting, is actually, so the Debian packages and RPM packages that we have in the repository are very, very mid. We're like very basic, and there is a lot that you can do. Like a dream that we have is that one day you would just be able to do apt install OpenTelemetry, and then all your applications on your Linux host are instrumented to the best of the opportunities. With no access to root, nothing, it should just work. There are a few requirements for what we want to achieve. So having like one button and it just works. It should have an amount of composability with the OpenTelemetry collector. So if you run on your EC2 host a collector nearby, the application should automatically talk to it so that you have one place to manage configurations, like authentication tokens for your APM backend or whatever. We want to make it to treat the configuration, declarative configuration format that there is going to be a talk about it later today, I believe, which is very exciting as kind of a first-class citizen in this experience, which requires collaboration from the packaging. And there are like if you're working with a commercial vendor for OpenTelemetry, you know that very often there are commercial distributions. And for example, the Elastic distribution for OpenTelemetry, the AWS distribution for OpenTelemetry, and there are excellent reasons for vendors to do this, to be able to push patches and bug fixes and maybe instrumentations that they need, but the community doesn't want to embrace. And those effectively vendored SDKs, not instrumentations, should feel like something that you can swap in without going nuts. This, for example, in the Debian packaging ecosystem, will require a significant amount of modeling with requires, enhances, provides, and a bunch of different very, very fun stuff. And another thing is that if you are packaging for an operating system, so a Debian derivative, Debian Ubuntu, Mint, whatever, anything based on RHEL, you also want to create the right relations between your package and the system packages. For example, wouldn't it be nice when you do apt install default JDK, then it tells you, hey, would you want to install the OpenTelemetry instrumentation for Java so that it just works? That would be really cool. So this is what we want to reach, and we have some ideas, but we could also use some help, especially from somebody working, for example, at Debian, Canonical, Red Hat, or that has experience with creating non-trivial packages in terms of integrating it in upstream. And this being said, bring it on.
Thank you.